module 1, and that is differential equations, and in this video we'll cover the topic examples based on cases of particular integral. So as in my previous video I have discussed about the solution of differential equations. So actually the solution of differential equations consists of the two parts. Those are complementary function as well as particular integral. So these PIs are the solution for right hand side part of the differential equation, because we have the general form of differential equation f dy is equal to qx. So CF is the solution of this part where we take this f dy is equal to 0. Then we get the solution that is known as CF. And particular integral is the solution of right hand side part. So for particular integral we write like 1 by fd on qx. 1 by fd. fd is what? A polynomial of differential operator. Alright. So in this way we can find out pi. Yes, so here in this video we'll try to cover some more examples based on various cases of particular integrals. Right? First case I had discussed in the first video. Here as well we'll take one example and then we'll start for the next cases. Okay? Yeah, let's have one more example on case 1 where we have this differential equation d cube minus 3d square plus 4 times y is equal to e raised to the power 2x. So this case is our first number where our qx, means right hand side part of the differential equation, is of the form e raised to the power ax, right? So e raised to the power ax, here a is 2. Alright, so we'll follow the concept of pi, which is like this. Pi is equal to 1 by d cube minus 3d square plus 4. This is our fd. Okay, e raised to the power 2x is our qx. Okay, so in this case what we do, we just replace this d, which is differential operator, by the amount a, which is the coefficient of x in our function e raised to the power ax. Okay, so just have a look at this. If we put d is equal to 2, rather in place of d we are substituting 2. So I am having 2 cube means 8 minus 3 2s are 6. 2 cube means 8 and 3 2s are 6. 2s are, because it is 2 square. So that is 12 plus 4. Alright, e raised to the power 2x as it is. So as we look at the denominator, here we are going to have the value as 0, which is undefined. So what should be done in such cases? Whenever we have such cases where the denominator is coming out to be 0, always remember we are going to multiply here by the independent variable, and simultaneously we are going to differentiate this fd with respect to d itself, right? So I will differentiate it. So I am getting here 3d square minus 6d. Alright, e raised to the power 2x remains as it is. Once again, I'll replace this d by 2, which is coefficient of x in e raised to the power ax. So once again I am going to replace d by 2. So I am getting here x 1 by 2 to the 4 3 the 12 minus 12 e raised to the power 2x. So once again I am getting here the denominator as 0, right? So once again I'll multiply by the independent variable and differentiate this denominator as I'm getting here 6d minus 6 e raised to the power 2x as it is. Now once again I'll replace this d by 2. So I'm getting here x square into 1 by 12 minus 6, that is 6 e raised to the power 2x. So in this way we have reached to the result, that is x squared by 6 e raised to the power 2x. Alright, so such examples where you are on the way to find out pi, particular integral, and whatever be the case of pi, whatever be the form of function, when you are getting the denominator 0, you have to apply this concept everywhere. Alright, what is the concept? Multiplication by the independent variable and parallelly differentiation of the polynomial of differential operator fd with respect to d. Okay, so I hope this concept was new for you and it's clear now. So in this way we are here at the result, that is x squared by 6 e raised to the power 2x. Okay, alright. So I am deleting this, or I can leave it as it is. Next case of pi is when a right hand side function, sometimes we write that right hand side of the differential equation by capital X, or sometimes we can write that by qx. Whatever be the notation, our focus is on the type of the function present on right hand side. So here, if it is of the form either sine or cosine, then what we have to do? We have to replace our d square, which is the differential operator present in the polynomial fd. This should be replaced by minus a square. A is that coefficient of x present in the angle of sine or cosine. Okay, right. So this was for square. For d cube or differential operator having power as 3, this d cube would be replaced by like this. Here, let's understand. D cube can be written as d square into d, right? Okay, so d square is replaced by minus a square and d remains as it is. Okay. So here what we have to do? D cube would be replaced by minus a square into d. So this should be d here. Alright. Similarly, for d raised to the power 4, it would be replaced by plus a raised to the power 4. So for even powers of d, we are replacing alternate negative positive. A raised to the power is that which is the differential operator having. Alright. Okay, and the odd powers are written in terms of even into odd powers of d, and accordingly those are replaced in the denominator of pi. That is nothing but our fd. Alright. So just have a look how it works. Alright, so if we have our function on right hand side in the form of sine or cosine, it will happen only with the case where qx is of the form sine or cosine. Then and only then we are going to operate rather I must say going to find out pi, right, in this manner. Okay then, so d square is replaced by a square with negative sign. Okay, a is the coefficient of x present in the angle of sine or cosine. Okay, same thing is here. If f of minus a square, if f of minus a square after replacement we are getting as 0, then what we are going to do? We are once again going to multiply by independent variable into 1 by derivative of f d with respect to d. So we would be getting f dash d, and the function sine or cosine remains same. Alright. Yes. And same thing we do for the next or the other powers of d, whether it is sine or cosine. Alright. So suppose after applying this first step, we are getting f dash minus a squared for the 0. What would happen then? We'll once again multiply by independent variable. I'm getting x squared 1 by f double dash d on the function. Alright, so in this way we can continue till we are not getting any fixed finite non-zero value in the denominator. Then and only then means then we'll be continuing, okay, with the same process, and same would be followed for cosine as well. Alright, I hope I'm clear till now. Let's continue. Yeah, let's have a look at this example. Here we have to find out pi of this differential equation. So here our differential equation is mentioned. Alright, so in symbolic form we have written like this: dq minus d squared plus 4d minus 4 is operated on this function dependent variable on sine 3x. So we have to find out the pi for this differential equation. Alright then, pi would be written like this: 1 by d cube minus d square plus 4d minus 4 sine 3x. Okay, so what we have learnt here, d square would be replaced by minus a square. Alright, what is a here? It's 3 here. So d square would be replaced by minus 9. Minus 9 or 3 square, I would say. It's taking time to write. 3 square I can write here. Alright. Okay. So this becomes, and d cube would be what? D square into d. So d square is what? Minus 9. D remains as it is. So I want to show you that what will happen with the powers of d only. Means only d having power 1, how we are going to further simplify it. Alright, so when I substitute in pi, what I am getting? 1 by d cube is what? Minus 9d. D square is what? Minus of minus 9. Right, plus 4d remains as it is, minus 4 as it is on sine 3x. Alright, so we'll take this d along with So I'm having 1 by 9 minus minus plus, right? So 9 minus 4 gives me 5, right? And minus 9 plus 4 gives me minus 5t on sine 3x. Alright, what would happen next? We have to rationalize whenever we have such results in the denominator. Okay, so rationalize means we'll change the sign of the factor, and I'm having 5 plus 5t divided by, it will be 25 minus 25 just a minute. Yes, minus 25d square. Alright. Okay. Function remains as it is. Sine 3x. Okay. Once again, this d square will be replaced by minus 3 square. Alright. So I'm having what? This minus 3 square into minus 25 becomes 75. 75 into once again 3. Alright. So we'll multiply this. 5 I can take common, or this becomes 1 plus d divided by 25 plus 25 into 9. Alright, and the function remains as it is. So in the denominator, what I'm getting? I think it is 250. Alright, 250 and 5 will divide. So 1 by 50. Okay. And 1 plus d means sine x, sine 3x as it is, plus differentiation of sine 3x is 3 times cos 3x. So in this way we can find our pi. Alright, so I hope it will be clear to you. Yes, because very slowly we had solved it. Okay, yeah. So this is the result. I can show you here. Yeah, this one with the, I've already shown you the simplifying. So this circled value is the result. All right. Okay. So now next case is when right hand side part qx or x is of the form x raised to the power m, where m is a positive integer. Alright, so how we are going to find out its pi? Okay, so pi standard form is pi is equal to 1 by fd x raised to the power m. How we are going to solve it? In the next slide, I am going to explain it. Right. So whenever we have our right hand side part qx as x raised to the power m, then always we are going to make the denominator of pi, that is 1 by fd, as any series which is of the form either 1 plus x or 1 minus x. So I will take this in terms of phi d. Alright, phi d inverse. Okay, so our aim is this. So let's understand this with one example. Find pi of d square plus 5d plus 4y is equal to x square plus 7x plus 9. Okay. Yeah, so let's solve it. 1 by d square plus 5d plus 4, the denominator as it is always, and here our function is x square plus 7x plus 9. What we have to do? We have to convert this given polynomial to in terms of series like this. Okay, so here we have taken the lowest degree term out. Lowest degree term will always be taken out so that we can form a series. Alright, so 4 is taken common. So I'm getting this 4 here. So this left inside the bracket is 1 plus 5d by 4 plus d square by 4. Alright, so these two terms will take along with, and I'll take this bracket to the numerator as I'm going to have 1 plus 5d raised to the power minus 1. Okay, so that I can expand it using appropriate expansion. Alright, so this is 1 plus 5d raised to the power minus 1, and this is our function to which it is going to be operated. Yes, so 1 minus x plus x square minus x cube plus x raised power 4 minus x 5 and so on. This is the expansion of 1 plus x raised to the power minus 1. Alternate positive negative sign. Alright, so here we have expanded till we are getting the term of d square. Why? Because the given function can be differentiated at the max 2 times. Third time it is going to give us 0. So that's why we will expand our series till we are getting the term of d square. And all the d square will collect and rest derivatives will give us 0. As we know that our function is having highest power as 2. Alright, so maximum 2 times it can be differentiated. Okay, so 1 minus this term is expanded here, 5d minus 4 minus d square by 4, and from here as well I'm going to have at least one term which is having d square. So that is nothing but the square of this term. It's 25d square over 16, and rest the terms we'll leave because these terms are not going to give us any value. Alright, so we have simplified a little bit and then applied, then operated on this function. These operators are applied, right? So with this one, I'm going to have the function as it is x square plus 7x plus 9, right? Minus 5 by 4 as it is. D is operated on this function. D is differential operators. 1 times this bracket would be differentiated. Okay. Plus 21 by 16 kept as it is, and now what is done? This d square is operated on x square plus 7x plus 9. Alright, okay, let's simplify this. This first bracket remains as it is, minus 5 by 4 remains as it is. D means once it is differentiated, so I am getting 2x plus 7 here. Of course 9 is going to be 0. Plus 21 by 16. So I am now going to differentiate this bracket 2 times. Okay. So twice it will give me 2 this term, and twice it will give me 0, and 1 give me this 9 is giving me 0 after double differentiation. Alright. So in this way we have reached to all the functions, and then further we can simplify it, collect the coefficients of x square, collect the coefficients of x, then collect the common terms. So as a result of which we are getting this as the result for pi of this differential equation which is mentioned above, right? Okay, let's solve this example for pi. Here as well, the concept of same, here factorization is used for finding out the pi, as I have already mentioned in the previous example. Alright, first example which we had solved, that was based on the same concept. Alright, so here this is e raised to the power ax into b, and we have taken this e raised to the power ax on left of the 1 by fd, and parallelly d is shifted by the amount to 1, so this becomes d plus 1 everywhere where d was, and then this e raised to the power x is written already here. Now it will behave according to cos 2x. Since a is 2, so we'll replace this d square by minus a square. Alright, and then we are left with this factor. Now we'll rationalize it with the opposite sign, and then further we have formed here the term of d square, and then we'll substitute this d square once again as minus 2 square, and in the denominator we are having the factor of 2 minus d. Okay, so in the denominator I am getting this 4 plus 4, that is 8 2s are 16 here and here, and 2 cos 2x, d cos 2x gives me differentiation of cos 2x. Alright, so after differentiating this I am getting with plus sign result 2 sin 2x. So in this way we can find out the